Good afternoon, everybody. Welcome to the session now entitled LLDB for your hardware, Remote Debugging the Hexagon DSP. So before we get into the main body of the session, I'll give some introductions and then we'll get into how you go about adapting LLDB, the why and how, the 3 steps you should use, and followed by a summary and a Q&A. Now, I'd like all questions to be kept until the end. And when we get to the Q&A, you just line up at the mic over there. It's not a roaming mic, just go and use that there. That'd be fantastic. So, the introductions. I'm the Games Technology Director for Codeplay software. And the job title is a little bit confusing, but Codeplay's background is really in games technology. So previously we'd worked with things like the PlayStation 3, PlayStation 2, and lately I've been personally involved in working with all our debugger projects. So the past 18 months I've been working on LLDB projects. And before that, I was actually involved with writing a debugger for the PlayStation 3 that used our single source compiler toolchain. And anyone here, I don't know if anyone's familiar with the PlayStation 3, but there's 2 specific architectures. And this debugger was specialized in the way that you could actually single step across CPUs. So you could single step from one function on one CPU into another function, which is running a completely different architecture. And that's where Codeplay are like experts in, heterogeneous compilers. We're 35 talented engineers and we're based out of Edinburgh in Scotland. So you'll probably be expecting that if you're coming to the European conference next year. So, not like here, pack a jumper or we work primarily on R&D, self and externally funded, work for hire, and that we create things for customers. They then own everything. Games firefighting as well, coming in the end of a project to get things up to frame rate. And we're really involved with standards bodies, so we're chairing a working group for OpenCL with Kronos and HSA Foundation and the Runtime working group. R&D is the R&D we do is we're doing some self-funded work in the next generation consoles and externally funded things like EU funding with Framework 7 grants. We do a lot of work with low power graphics technology, and that's what we're doing there. But get to the main point here is why am I talking about Hexagon? And the reason is that Codeplay is creating an LLDB-based debugger for the Hexagon DSP. And I'm not really going to go into that much detail about the DSP, the chip itself. A variety of information is available on Qualcomm's developer portal, and you can request information to that through their online portal. Other than that, you can go back a couple of years and find a talk by Taylor Simpson, porting LLVM to next generation DSP, and he goes into some detail there. It's a really good talk. You should really make sure you see that. The development of this is still ongoing. We're quite in the early stage, but at completion, we're a remote debugger with Linux and Windows hosts with Eclipse integration. So this talk is really about adapting LLDB, and I'm just giving Hexagon as an example, because it's always good to be able to back up what you're saying with a real-world example. So why would you want to get LLDB on your hardware? And debuggers are an essential part of any SDK, as everyone knows. And your client, your customers, your licensees are demanding fast debuggers with new and exciting features. And LLDB is the perfect balance of performance. It's got a really nice clean architecture that you can extend. And it leverages a lot of code from LLVM. So if you're already working with LLVM, get your compilers, it's an ideal match. Lots of other reasons. How you go about it? Well, think there's 3 steps to debugger implementation. There is the binary, the thing that you're running on your chip, and it's debugging information. So it's getting that binary into a debugger, loading it, the debugger understanding what is in there. The second one is your target system. And you need to be able to inspect state from that target system, and then, given that state, tell it what to do next. So you need to control the system as well. The third step is kind of like intermixing the previous 2. So you need to take the debug information, and you need to take the state and control of your target system, and combine these in order to allow the creation of, advanced features in your debugger. And it's step 3, which really is the difference between, bottom line debugger, just as low as you can go, really, and a useful debugger that your customers are going to want to use. So, as with all things computing, there's actually another step, which is LLVM and client support for your target hardware. Now, you can hack around this in certain ways, but you really do not want to. The disassembler is taken straight from there. And for those interested, the Hexagon disassembler is currently in development by Qualcomm Innovation Center, and this will be upstreamed. So that's fantastic. For expression evaluation, etc., you need to ensure that your Clang or other front end in there has those language features enabled. You want to debug the correct language. So, for example, if it's maybe OpenCL or like GLSL or something like that, all the intrinsics, you want to be able, the expression evaluator, to know those intrinsics so that you can actually run that in the debugger. And this is another reason why your compiler team should be staying as close to tip as possible. Getting older versions of Clang and LLVM to run with LLDB is a lot of work. I've had to do it for a project, and it's a lot of time taken up. So, and the issues that you get are the sort of issues that will only raise their heads at the worst possible times. So stay close to tip, and you'll be good. Hexagon tracks tips, so we're into a winner with that. So finally into the meat here. Step 1, getting your binary loaded into the debugger. So sections, symbols, and the debugging information. And LLDB already supports ELF and Mac objects. In terms of debugging information, Dwarf supported, and features are being added all the time if you look at the commits list. My experience personally is only with ELF and Dwarf. I know there's kind of cough support in there, but I think in terms of debugging information, it's not really there just yet, especially on Windows. If you're not using a supported format yet, you want to look at the object file classes, and you can use the ELF one of those as a baseline. It's fairly well laid out, and you should be able to work out how to edit it to your particular standard. Hexagon, it's both ELF and Dwarf, so job done, right? Sadly, we still need to do a few things just to line up the binary, so LLDB knows that its target is Hexagon. So the definitions are actually really fairly simple. Talking ArcSpec, CPP. Obviously, this is just there just to give you a little example. You just add lines like this. You need to edit the core definitions, the ELF architecture entries, and function cores match. You really want to implement that. That is a function which is very useful when you have an architecture with several versions which are compatible with each other. So with Hexagon, there's several versions that are compatible in certain ways, and we want to implement that in there. A function which kind of looks a little bit odd for being in here already is getUnwinder. You want to add your architecture to that, because if you do not, you will end up with an invalid object getting returned from that. So you need to implement that, and best do it now to save in the pain later. So that really is it, actually. If your target has LLVM already implemented for it. You can just launch LLDB and create a target. So launch in an example binary hello sample, and you see there it is set to Hexagon. As an aside, all of the things I'm doing here with LLDB, this is all running from the Windows front-end driver. Don't know if you already know, but we committed Windows support for that now, so you can actually get a command line interface to LLDB on Windows using Visual Studio 13 now, which has been missing for quite some time. So once you've loaded that, you can inspect images, the sections here. And the thing you really want to look at here is to ensure that the debug info section names have the correct types. So the dwarf line one lines up. And once you've done that, you can do things like inspect the line table. So you will get the addresses of certain lines to map for source debugging. And even now, at this early stage, we can create breakpoints. So just go in, set a breakpoint in hello.e20, and you'll see that that address actually matches what we had previously, which is great. But when you try and set a breakpoint on the main function, you'll see that it's slightly different. But there's a reason for that, and actually it's because LLDB has loaded in the debugging information, it's parsed it, it's done its job, and it has actually set the breakpoint not at the symbol name, it's set it after the function prologue, so after all of the ABI magic. So things like your arguments, etc., and locations accessible for the debugger. So once you're at that point, you've actually got enough information in the debugger to progress. Your hardware may have additional information sections, relocations, etc., that may need to get implemented. But once you've done that, you've got to that level where you can set a breakpoint and it gives you an address, then you can continue and you can add those other features as and when required. So that's step one done, and we can progress to step two, which is control and state. Control and state of the target system. Now there are two routes for this, the local debugging route and remote debugging. And local debugging already has support for OS X, Linux and FreeBSD. This is the standard debugging architecture where you're locally debugging things on your big computer. For a DSP or any other embedded system, we do not want to run the debugger on chip. And at that point, we're not really going to be looking at any local debugging here. If you were wanting to implement a local debugger, there's 3 targets there. Should be fairly easy to see how things match up, and you go in and implement that yourself. Remote debugging is usually over TCP, a serial connection, or more lately TCP over USB with all these consumer devices that have USB connections. For Hexagon, remote is ideal, and LLDB has support for the GDB remote serial protocol. And if anybody's used GDB with GDB server, that is what you're using. So just give a quick crash course on RSP, simple client server architecture. What is transmitted is ASCII, so you can read it if you're logging it, and it's packet-based. So just going to give a quick example here. Client sends, server sends. It's fairly straightforward. So HCO is setting thread to 0. We're setting a breakpoint. You can, depending on that number there, you can actually set software breakpoints, hardware breakpoints. If your hardware supports hardware breakpoints, use them. And you can continue execution. So this is basically setting a breakpoint, hitting a breakpoint. We're reading some memory here and getting it back. And then we continue, and we've stopped with a seg fault. So S, that's hex, so it's 11, so seg fault signal. So that's simple crash course. And for remote debugging, this stub, which runs on your actual target hardware, you want it to be very, very small whilst allowing all of these features. So you want it to read and write memory, registers, give the thread states, etc., and breakpoint setting unset, amongst other things. But this is a really important point here. It needs to be small as possible. You should not be, loading debugging information on your remote stub. The whole point we're using remote debugging is because we're on a constrained resource architecture. It's just simply for target control and state inspection. We don't want it deciding where breakpoint should be. LLDB and the host will decide on that. So remote debugging with LLDB is quite well supported, actually. It's got GDB remote support, and there are 3 server options. These servers are actually two of them, the debug server and LLDB platform, part of the LLDB project. They're in the tools folder. And I'll just go through these. So they basically run on the target device and transmit to LLDB on the actual your computer, your main computer. Debug server, the feature page for it states OS X debugging only. It's a manual process. You open a shell to your device, you start up debug server with a port to use and an executable to debug, and it waits for LLVM, LLDB to connect to it. It could be ported. We have ported it before to another target. It's not ideal. You do not want to be doing this. But thankfully, the focus is not on debug server, it's on LLDB platform. And this is designed as a daemon, a service, and it services actions such as listing processes, transferring files, attaching to processes, and actually starting the debugging sessions. So the development of this is gaining momentum, but it's still quite early. If you're going to port anything, port this, because in the longer term, you'll be very happy. You actually don't need to do that much to port it, actually. It's fairly straightforward. You just need to set up a host. So you need to port all the host functions. And it uses the GDB remote communications server, which is in there, and it's cross-platform, uses the host. For a third-party server, you may already have this if it's already an established chip. This is the case with the Hexagon simulator, and we want to leverage that as much as possible. So the main problem with doing this sort of thing is you need to watch out for divergence from the RSP standard, or things that have been added to facilitate specific features of your hardware. These extensions creep into the system, and it's perfect when you control both ends. We want to ensure LLDB is updated to understand these features because they're there for a reason. And LLDB itself has extensions. The traditional GDB and GDB server relationship has been quite nasty if you've got mismatched versions. So for LLDB, there's new extensions to try and aid this. They're all documented very well. There's just a text file in the documents folder. You can read that and figure out where it's going. The main one, or one of the main ones, is the target register set. So LLDB actually queries to get the target register set of the server. And if you're using maybe a third-party server, you might not have that extension enabled. And previously, if this was the case, you would have the register set kind of encoded, hard encoded into the source code. You can see it's been done there with ARM if you look in the source. And now there's a new thing that's been added just recently. I had to update the slides for this. So you can now do this via a Python script. So you can just set this target definition file. It's just a Python file, and it can set your register set. It's fairly good. There's an example, the x86 one, and you can have a look at that. So one thing that would be really nice for LLDB would, if it would had a plugin system for the remote system within it. from the client's perspective if you're trying to work with third-party servers. Because at the moment, it's just like a massive case statement, really, in the source. And ideally, you would want to have a fall through which then queried this plugin system and said, hey, do I have any classes here which can facilitate this packet? And if we had that, that would be very useful for debugger developers. And it's something that we'll actually be looking at for Hexagon, because we don't really want to mess up slash kind of make the base, the RSP implementation that's in LLDB. We don't want to kind of dirty it with target-specific things. We want to keep that nice and clean, and then if we had a plugin system that we could put all the target-specific stuff into, that would be really good. So at the moment, we're still at step 2. We've got control and state of the target system. We can see the status of the target, we can control it, we can read write memory, etc. And that's kind of enough. But you want some extra stuff for if you want a useful debugger. If you were to release that sort of debugger to your customers, they wouldn't be very happy. So can you pull files from your remote target? It's a very useful feature, as we'll come to see later. And the remote debugging aspects need to be kind of tied up with the process so that this architecture, the Hexagon architecture, we know that it's a remote process and can use the remote system. And this is done via the platform plugin. Now, this has got all the methods for actions like launching processes, attaching processes, and yeah, they've supported part of it is very important. If you don't support launching processes, then we need to, show that to the user in a very nice way. They're already debugging a very hard problem. They don't need their debugger to be giving them cryptic error messages. The architectures they support, and you can see the GDB server for an example. Additionally, you want to update the process plugin, and this kind of directs all the various read memory, resume process functionality to whatever you need it to be. And for a remote process, like for a remote process, remote architecture, that the GDB remote one should actually be enough for your general requirements, and you could add things to it if your architecture needs it. And this actually does waiting for responses, which you would think that's really quite bad. But like I said from at the beginning, LLDB has been designed from the start to be multi-threaded for performance, and this means you can wait there, and the user experience isn't going to suddenly go, oh, I can't type anything into this shell. It's going to be okay. So remote debugging, we can control the target system, and we can create its state. So step 2 is done. Now, at this point, you can set breakpoints. You can view memory and registers. You've got source debugging for free, really, as long as the source is kind of in a location where LLDB can find it in its working directory. Other features that could possibly work, step over single step. Step into single step in some situations if your hardware has hardware single step. And some variables could be viewed, maybe global variables, etc. But your user goes, debugs a dynamic library which is loaded at runtime, and then you realize that you have lots and lots of things to implement before your debugger is actually usable by your customers. So step 3, the hard part. Taking what we've learned from step 1 and 2 and using the information from both of those steps to actually implement the features that people expect from a debugger. So dynamic loaders and linkers. The debugger needs to track these shared libraries. So whatever operating system or dynamic loader you use should have an API that debuggers can use to inspect state. LLDB uses an additional packet. In this case, it's one of the extensions, the shared lib info adder packet. And you can use, like the Linux dynamic loader uses that to traverse known data structures, and it can read things out to see where these files should be, and then it can pull those files over. And that's why pulling files from the target is very important, because if you've got a dynamic thing that's loaded, we can then pull it over to LLDB and then load its debugging information from step 1, and then debug inside it. So if your target doesn't have shared libraries, it's all static, then you probably don't need this. But you can look at the POSIX dynamic loader there, and yeah, it uses the process and image info address, and obviously when you're using the remote process, it just sends a packet. So you can see it's kind of like a proxy, the remote one. It doesn't really do anything locally at all. It's all sending packets over the network. Now, Hexagon does support dynamic loading of shared libraries, and we'll be adding support for this later. Like I said, the project's still quite early, so we're not right into step 3 yet. But it's based in the System V ABI data structures. So that's when you're implementing this sort of stuff, that's when you get your big documentation of all your ABI and everything, and read it religiously. So, next, the ABI for your argument passing, your function returns, what registers are volatile, etc. And without this, the debugging experience it won't be great. You'll get weird things happening. You can just have a look at the OS X one for ARM, and you can actually use that as a base. I've done it before for a Linux ARM target. I've just copied that, and very minor changes, and it actually worked enough to use as a base. So if you're trying to debug Linux on a remote ARM target, that's fantastic. You can use that. For Hexagon, we'll be implementing our own ABI classes for this. Like I said, early stage, so we haven't done much on it. Call stacks. This is when we get into the nasty part. If your debugging information is of high quality, includes call frame information, where things are located at various frames, that's good. If your ABI always specifies a frame pointer, and your users aren't using compilation options which omit them, that's great. Without CFI, then you get arguments, registers, etc., not being able to get located, could be wrong. And then we get to the unwinding, and this is done via plan lists. Anyone who's used LLDB before looked into it, there's loads of plans, like step into plans, etc. And its general idea is finds frame pointer, if it's always defined, utilizes CFI in the debugging information. If all else fails, emulate. And emulator isn't just for unwinding, it's kind of also used for branch target addresses for things like single stepping. Thankfully, Hexagon has hardware single step support, so it isn't as important. But you can have a look at the ARM instruction emulator in LLVM to see just how large this stuff is. And whilst it doesn't need to be a full emulator, you only need to emulate the instructions which are maybe in function prologues, etc. But there are times when the users of the debugger will want to debug optimized code. So then you've got to actually look and see, are there any situations where those instructions could get optimized to something else? So you need to be able to emulate all of them as well. Like I said, optimized code. So, unwinding, instruction emulation, seriously, these things could fit a whole other talk. The main point is the interpretation of the debugging information in tandem with the runtime state is where the advanced features of debuggers lie. Developers expect these features now, and you need to devote a lot of time to these areas. So step 3 is not even close to being complete. It takes a very long time. So in summary, we have 3 steps. We get the binary loaded into the debugger. We adapt or port whichever remote server you choose, making sure to add to your platform and process methods where applicable. And the real meat of implementing your debugger is in step 3, dynamic loaders, unwinders, emulators, and the last 10% of your to-do list will take 90% of your time. So you need to really prepare and manage your resources with step 3 because it will take a very long time to get everything right. So LLDB is fantastic. It has a really good support for the most popular object formats. It's built-in support for remote debugging. But the remote debugging aspects of it, I'd really like to see some extendability in there, maybe a plugin system, like I mentioned before. And the advanced features people really care about means you really need to inspect the target state with your debugging information, act on it, emulation, etc. will all fall through from that. And yeah, I've not even mentioned IDE integration, which would be, again, a whole other talk. So again, in summary, steps 1 and 2, you'll get a bare bones debugger. It will be up and running, fairly straightforward, and it does progress really quickly. You can, be there in weeks to a couple of months of work. For step 3, that's going from a bare bones debugger to a great debugger, and that is another matter. You're talking months to years of man-hours. So with that, thank you very much I hope people got some information from that. I'd really like to thank Qualcomm Innovation Center for allowing me to use Hexagon as an example in this talk, because Codeplay as a company is usually under a mountain of NDAs. And whilst we do work in very interesting things, never allowed to say it. So thank you very much to Quick. And I'd quite like to open the floor to questions. No questions?
Oh, I'll ask one.
Oh, I thought I was going to say, I've explained absolutely everything possible with debuggers.
Yeah. One thing I would like to know is what experience have you had with things like conditional breakpoints and actually jitting the conditional expression on a specific target? Do you have a...
Conditional breakpoints, what our experience with that has just been that they kind of just worked once you implemented it all. I don't think there was any JIT stuff in there. I mean, you've got Python integration, which is really great, so you can actually run the Python script as you hit a breakpoint and decide whether you want to stop or continue. We have obviously done JIT stuff. The expression evaluation can JIT and then push the code over to the device and run there. Okay. So we have used JIT and we have used conditionals, but I don't think we've used them at the same time. That probably doesn't answer your question. Right. But we haven't really had any experience of them of using the JIT stuff for conditional expression.
But it never happened automatically. If the condition can't be handled by the IR interpreter,
yeah.
Then a JIT will occur.
Mm-hmm.
So it's no different from expression evaluation.
Yeah, right. Okay.
But the expression evaluation on the target needs memory allocation on the target, and that's part of the porting process.
You've got to be careful also if you've got execution protection on there to make sure you can actually, write your instructions into memory. Any more?
You didn't mention watch points.
Yeah. The architectures that we've really used in previous implementations, We haven't used them. But, I mean, again, it's just fairly simple to implement. Especially with remote, there are watch point types in the packetization that's sent over the network. So as long as it's implemented in the server and then you use it, it should be okay. Okay. Thanks.